This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing extended surfaces, that is the fins, in heat and mass transfer subject. The amount of heat energy which is flowing from the fluid to the surface is given by the Newton's law of cooling equations, that is Q is equal to H into A Ts minus Tf, where Q is representing the magnitude of heat energy that is transferred from fluid to the surface, which is maintaining at a temperature of Tf. H is equal to coefficient of heat convection process. A is the surface area. It is obvious from this equation that in order to increase the rate of heat transfer from fluid to the surface, we can increase the heat transfer coefficient to R, the surface area, or that is the difference of temperature Ts and Tf. But the amount of heat transfer generally enhanced by increasing the area of heat transferring surface as shown in figure. Why? Because there is a limitations, the temperature difference of Ts and Tf, because the temperature of the hot fluid remains constant. Tf is also, that means almost the object temperature which is having contact with the hot fluid also remains constant. Hence, in most of the cases, somewhat difficult to increase the values of Ts minus Tf. Area is also having area H is that is coefficient of heat transfer by convection process. It is also for particular media it is remains constant, and so this value is somewhat difficult to increase. Only one option is there for increasing the flow of heat rate from the fluid to the hot surface can be increased by increasing the surface area, that is the A value. In order to increase the transfer area is achieved by attaching certain protrusion to the hot surface. These protrusions are referred to as fins or sometimes pins, and made up of materials having high thermal conductivity such as aluminium. A considerable enhancement in heat transfer rate from a solid surface by exposing larger area for convective as well as the radiative heat transfer. Here example I am taking now. Here energy is there now, it is flowing now, the surface. This energy should be dissipated to this air outside for cooling point of view, particularly in automobile sector or in transformers. The heat energy which is generated just within the cylinder in automobile sector, that should be transferred to the air now, so to the atmosphere. So in order to transfer with the higher rate, the body should be exposed with certain protrusions on the hot solid surface, generally made up of material which is having high thermal conductivity, example aluminium. Here this is the object is shown now, this is the object now. Here it is having certain protrusions now, that is called projections. This is perpendicular to the surface in order to increase the surface area now. So this is one of the efficient method for dissipating the heat from the body which is having higher temperature to the environment. The main application of fins we found in transformers and motor engines, scooters, motorcycles as well as the compressors. The fins are used when convective heat transfer coefficient is low to enhance the heat transfer rate now. In engine cylinders of scooters and motorcycles, condensers and evaporators of refrigerator systems, car radiators, these fins are used to give the engine set almost nearer to the atmospheric temperature. Depending on geometrical features, the fins are classified into straight fins. The straight fins are almost these are perpendicular to the surface to which it is attached as shown in figure. These fins it may be in a rectangular or it may be having just a taper in cross section as shown in figure. The term straight fins is applied to the extended surface attached to a wall or the plane almost perpendicular to it now. The annular fins now. The annular fin is the one attached to the circumferentially to a cylindrical surface as shown in figure. Okay, this is known as here now annular fins now. Almost it is in the form of circumferentially. It is a concentric circle. It is nothing but similar to the. It is attached to the cylinder shown in figure. And spin and pin fin. It is an extended surface of the cylinder or the conical shape as shown in here figure. Here, this surface is there now. It may be in the form of cylinder or it may be of cone or truncated cone, which is extended to the flat surfaces shown in figure. That means that depending on the type of the geometric shape of the fins, these are classified as straight fin, annular or circumferential fins, or spline or pin fin. Heat transfer through a fin of uniform cross section. Consider rectangular fin of length L, width W. This is known as L, and thickness is equal to 2 delta. This is known as here thickness delta has been attached to the wall as shown in figure. So heat flow is along the length of the fin and it is surrounded by atmospheric air having temperature T. The temperature at the base root for the fin adjoining the wall is T naught. Here from this arrangement now, here this is this wall. Assume it is nothing but exposed to higher temperature. The temperature should be dissipated to the air in order to maintain this body at normal temperature. Here fin is attached to it, which is in the form of rectangular shape perpendicular to its surface. At the junction of fin to the surface, assume this is equal to here T naught. The dimension of the fins are having length is equal to L and width and thickness is equal to 2 delta. Let TA is representing the air temperature. Here the heat energy is flowing from the fin surfaces to the air by using conduction as well as the radiation as well as the convection process. Okay, in order to determine the flow equation, energy flow equations, here the assumptions are the flow of heat takes place under steady state conditions. That is, the Q is remains constant. That is, the amount of heat energy transferring per unit time remains constant. And it is a one-dimensional flow that is along the length of the fin. Because the energy can flow just in any direction, so, but according to the directions, the energy is flowing only one direction along its length. That is x direction. The thermal conductivity of the materials remains constant. Convective heat transfer coefficient H uniform over the entire surface of the fin. The temperature T naught, that is, it is at the junction of fin as well as the surface to which it is attached is the T naught at the base, or the root fin is uniform and is equal to the here wall temperature. Here consider a small element of thickness delta x at a distance x from the fin now. Here consider this is nothing but a small thickness having thickness is equal to here dx, you are taken now. At the distance of x from the base now. So the perimeter is equal to, the perimeter nothing but here it is equal to, it's called perimeter for the surface. That means which is equal to 2 into W, where W is nothing but represented width, here 1 and 1, and 4 into delta. 2 delta is represented the thickness, and so 4 into delta. Here when we are taking 2 is the common, we can take it as 2 into W plus 2 delta. The cross section area is equal to AC is equal to W into 2 delta. Surface area is equal to A is equal to P into delta X, where P is equal to perimeter and delta X. This is nothing but what we observe. That is P into delta X. Under steady state conditions, the energy balance on this element can be expressed as the amount of heat energy that is extracted from the wall by the fin should be equal to the amount of energy that is dissipated to the air by the conduction process as well as the radiation process. So the rate of heat conducted into the element at a distance of x, when you are taking it, x is equal to rate of heat conducted from the element at x plus delta x plus rate of heat convected from the element. Here we are considering this element only. The rate of heat conducted into the element when the amount of energy that is flowing at this point, it should be equal to the amount of energy that is coming out of this element by using conduction process plus the amount of energy that is dissipated by using convection process. So heat conducted into the element is equal to, here given by Qx is equal to minus of K into AC into dt by dx. Here which is equal to the heat conducted out of the element is equal to Qx plus delta x, addition we are taking, it is equal to Qx plus dy by dx of Qx into delta x now, or which is equal to minus of K into AC dt by dx from x to x plus delta x now. Heat converted out of the element is equal to, by using convection process, Qc is equal to h into A T minus T A, or which is equal to h into, here area is equal to delta x into P and T minus T alpha. That heat balance for this element what we consider is equal to Qx is equal to Qx plus delta x plus Qc, that is the amount of energy that is dissipated by convection process. Using these equations, we got minus of Qx is equal to minus of K into AC dt by dx, it is equal to minus of KAC dt by dx for the x to x plus delta x plus h into dx into p into t minus t n. From these equations, minus KAC into dt by dx from x equal to minus of K into dt by dx, here x to delta x plus d by dx qx delta x plus h into delta x p into t minus n now. So from these relations now we got to d by dx, it is equal to, because both are equal, get cancelled now. Here minus of KAC dt by dx into delta x is equal to minus of h into delta x p t minus t n now. From these relations, minus of Kc into delta x is equal to d2 square divided by dx square, because on differentiating dt by dx with respect to the x now, we got dt square by dx square, which is equal to h into delta x p into t minus tn, or k into ac dc square by dx square is equal to h into p into t minus ta. Let here t minus ta is equal to theta. Similarly, t naught minus ta is equal to theta naught. Now, differentiate the equations, this is 8 and 9 with respect to the x 2 times. We got dt by first term, dt by dx is equal to d theta by dx, and dt square theta x by dx square is equal to d square theta divided by dx square. That is from this relationship we are having. Using equation, this assume these 10 equations now. Substituting this equation 10 in 7, it can be written as k into ac. Earlier it is there d square t divided by dx square. It is represented as d square theta divided by dx square, which is equal to h into p into theta. So from these relations now, d square theta divided by dx square is equal to hp divided by k by kac into theta, or d square theta by dx square is equal to, we can put it this entire, this value is equal to m square theta now, where m square is equal to hp divided by kac, or m is equal to under root of hp divided by kac. Now the modified equation is, we can write it now, d square theta divided by dx square minus m square theta is equal to 0 now. So the equation number 11 is a governing equation, and its solution is expressed in the form of theta is equal to a into a mx plus b into a minus mx, where emx is equal to cos mx plus sin mx. Similarly, e minus mx is equal to cos mx minus sin mx. So theta is equal to, we can take it as now, that is a plus b into cos mx plus a minus b into sin mx. Theta is equal to, here now, c1 cos h mx plus c2 sin h mx, where c1 is equal to a plus b and c2 is equal to a minus b. The equation 2 represent as general equations. For solving this, what is the amount of energy that can be transferred by using conduction as well as the convection process through the fin. Here the constants C1 and C2 are determined by using the boundary conditions. There are 4 possible sets of boundary conditions, each giving a different sets of values C1 and C2. These boundary conditions and the solution for the temperature distribution for each case is shown in table. Okay, these are the here temperature distributions such as the boundary conditions. For general nomenclature is given. For long fin, when you are taking, that is x is equal to 0, then theta is equal to t naught minus t alpha. So from this relation, t minus tw divided by t naught minus t alpha is equal to e to the power of minus mx. When the short fin is there and its end is insulated, we can take x is equal to 0, theta is equal to t naught minus t alpha. Similarly, x is equal to L, we can take dt minus dx is equal to 0. So from this relationship we got t minus t alpha divided by t naught minus t alpha is equal to cos h m into L minus x divided by cos h ml. For the short fin, convection at the tip hi is considered, that is x is equal to 0, then theta is equal to t naught minus t alpha, x is equal to L into minus of Ka into dt by dx divided by L. which is also equal to the amount of heat energy that is dissipated by convection process, that is HL into A TL minus T alpha now. So from these relations we got T minus T alpha divided by T naught minus T alpha is equal to cos HM L minus X plus HL divided by MK sin H into M L minus X divided by cos H ML plus HL divided by MK into sin HML. Fixed end conditions, that is X is equal to 0, theta is equal to T naught 1 minus T alpha, X is equal to L, theta is equal to T alpha 2 minus Tm. So T minus T alpha divided by Tbn minus T alpha is equal to Tb2 minus T alpha divided by Tb1 minus T alpha multiplied by sin H mx plus sin H L minus x divided by sin H M L. Okay, these are the boundary conditions as well as the temperature distributions is given. The C1 and C2 values can be evaluated by using these four boundary conditions. Okay, this content is extracted from this following textbooks as well as the references. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.